We should be a little careful about our definition of expectation in the case when x has infinitely many values, because then we have an infinite sum, and those aren't always well defined. For those of you who haven't seen what that might mean, I'm just going to give a very rough overview of the math involved to explain a condition that you will see as part of the definition of expectation. And so we'll start by looking at just an ordinary infinite sum of numbers. And first recognize that this thing that I've written down is actually notation for a limit. It's a limit of finite numbers. So you add your terms, but you go to n. That's a finite sum, so that's a number. And then you go to n plus 1 and n plus 2 and so on. You just keep going. And if that thing on the right-hand side converges to a limit, then you have your infinite sum. Now, why might the limit not exist? Well, you can certainly imagine that those partial sums could shoot off to infinity or to minus infinity. But if the terms ai are both could be negative or positive, then the sums can oscillate wildly. All kinds of interesting stuff can happen. So you need a condition so that those sums are actually, the limit is actually finite, and the behavior of your series is what you'd want it to be. And one such condition is absolute convergence. And this says that if you can add not just the terms themselves but their absolute values and get something finite. So let's take a look at what's happening there. This infinite sum, if you think of the partial sums going up to n, then n plus 1 and so on, those are going to be non-decreasing. So they might shoot off to infinity, but they're not going to oscillate, they're not going to wobble all over the place. If they don't shoot off to infinity, if they actually end up somewhere finite, then the sum that you really want behaves as you want. It's finite, and moreover, it has the same value regardless of which order you add the terms in. That we take for granted when we have finite sums, that we can do them in any order. When you have infinite sums, you can run into trouble, except when you have the condition of absolute convergence, then you're safe. If you want to know why all this is true, please take a class in real analysis. What I'd like to do is see what this means for the sum that we're doing, and our sum is this one here. So the generic term in our sum is x times the probability that the random variable has that value. So the absolute value of the generic term, well, the probability is already non-negative, so it's only the value itself that might be negative. So we put the absolute value just on the x. And so now our absolute convergence criterion says, and we're ready to give a very formal definition, if this sum is finite, then expectation is well defined and has the definition that is so familiar to us. And if that condition isn't satisfied, then your expectation isn't defined. And that's a little unnerving. But in this class, you can be reassured that virtually every expectation that you compute will be well defined. You don't have to check the condition. Occasionally, there will be very interesting random variables that don't have expectations. And we'll flag those and we'll study those in particular. If you're an economist, then you will frequently encounter distributions that have enough probability out on the very large values that the existence of expectation becomes a little dicey. So it is good to be aware that there's something that needs to be taken care of, but also to know that in this class, you don't have to take care of it until we ask you to.